Welcome to today's chemistry lecture. In this lecture, we are going to discuss our two remaining topics from this chapter, which are calculations based on chemical equation, and the second topic is limiting reactant. Plus, we will see them with their example. Also, we will seek upon the constructed response question from our exercise. Here comes our first topic, which is calculations based on chemical equation. A complete and balanced chemical equation tells us the mole ratio or mass ratio between the reactant and the product. Means a chemical equation will used to find the mole ratio or mass ratio that would be present between our reactant and product. With this help, we can find masses of the product of the given masses of the reactant or the masses of the reactant from the given masses of the product. Means we can find our reactants mass from products and our products mass from our reactants. For example, that 1 mole of calcium carbonate, which is 100 gram, will react with 2 mole of hydrochloric acid, which are 73 gram, to produce 1 mole of calcium chloride, which is 111 gram, and 1 mole of water, which is 18 gram, and 1 mole of carbon dioxide, which is 44 gram. By looking upon the equation, we can see clearly the ratio or the mass ratio that present between the reactant and the products. Here comes our example for calculations based on chemical equation. Example states that 25 gram of limestone react with an excess of hydrochloric acid. According to the above equation, how much calcium chloride will be produced? Let's see the solution. According to the equation, in first step, we will see that how many of produce calcium chloride from 100 gram of limestone. So 100 gram of limestone react to produce calcium chloride, which is equal to 111 gram. So 1 gram of limestone will react to produce calcium chloride. By dividing with 100, we can find the 1 gram. 25 gram of limestone will react to produce calcium chloride. By multiplying our value with 25 gram, we can find our answer, which is 27.75 gram of calcium chloride that will be produced by using our given balanced chemical equation. Here comes our quick check problem, which states that why it is necessary for a chemical equation to be balanced before it can be used in calculation. So answer is that a chemical equation must be balanced because chemical equations rely entirely on the law of conservation of mass. This fundamental law states that matter can neither be created nor destroyed during a chemical reaction. So that's why a chemical reaction equation is necessarily to be balanced before it can be used in calculation. So if an equation is unbalanced, the mole and mass ratio between the reactants and the products will be incorrect. Balancing the equation ensures that exact number of atoms of each element is identical on both sides of the reaction, providing the precise mathematical properties needed to perform accurate stoichiometry calculation. Here comes our second topic, which is limiting reactant. So first of all, we will see the reality of chemical reaction. In a perfect theoretical world, reactants are mixed exactly according to the stoichiometry ratio shown in a balanced chemical equation. However, in the real world, laboratory experiments and industrial processes, this is rarely the case. Most often, one or more reactants are deliberately used in a large excess. Why use an excess? Chemists intentionally add an excess of a cheaper, more abundant reactant to ensure that the other, more expensive reactant is entirely consumed. This maximizes efficiency and prevents costly chemicals from going to waste. Here comes some definition, the key terms. When a reaction runs its course under these conditions, we categorize the reactant into two groups. First one is excess reactant and the second is limiting reactant. The excess reactant is that the chemical that is left behind or remains unreacted at the end of the chemical process, while the limiting reactant is that the reactant that is consumed completely and earlier than others because it runs out first. It is the limiting reactant that ultimately controls and dictates the total amount of product in a chemical reaction. Now we will see how to identify a limiting reactant. To successfully identify which starting chemical is your limiting reactant, you must methodically follow these three core steps. First step is calculate the number of moles of each reactant based on the starting masses or amounts provided in the problem. The second is calculate the number of moles of product that could theoretically form from each individual reactant's calculated moles. Third, compare the results. Identify the reactant that yields the least amount of product. That specific reactant is your limiting reactant. Plus, also, this is the answer of our first constructive response questions, which we are going to study now. The first question was, how would you identify the limiting reactant in a chemical reaction? So these 3 points briefly discuss that how we identify a limiting reactant in a chemical reaction. Our second question is, why is it important to find the purity of a compound which is used as a medicine? So answer is that it is very important to find the purity of a compound used in medicine because impurities may be harmful or toxic. Impure medicines can give incorrect dosage, reduce effectiveness and can cause side effects. The percentage purity of a medicine causes that medicines are safe, effective and reliable for patient use. Here is the third question, which is, will there be a limiting reactant in a reversible reaction? So let's see the answer. The reactant which is consumed earlier is called limiting reactant. It may also be defined as the reactant that produces the lowest mole of product in a reaction. Limiting reactant in a reversible reaction. Reversible reactions are those reactions in which reactants are not completely converted into product. The limiting reactant controlling the amount of product formed, but in reversible reaction, as no product is formed or reactions are incomplete. So there is no limiting reactant in a reversible reaction. Our fourth question is, how do you know if a formula is empirical formula or not? So let's see the answer. We can know whether a formula is empirical or not by checking the ratio of atoms in the formula. Identification of empirical formula. Step 1. If the simplest whole number ratio is found between the atom of an element, then formula is empirical. For example, CH2O is empirical formula of glucose. If the subscripts into the formula can be reduced simpler further, then the formula is empirical. Our fifth question is, write down on method to find out the molecular mass of a compound without knowing its molecular formula. So let's see the answer. Determination of molecular mass without molecular formula. Normally, a molecular formula is written by multiplying its empirical formula with the number n, and the n is the ratio of molecular formula to formula mass. So, molecular formula is equal to n empirical formula, which is directly converted into n is equal to molecular mass divided by formula mass. There are few ways to determine the molecular mass without knowing the molecular form. For example, mass spectrometry, freezing point depression, boiling point elevation, and vapor density method.